Welcome. In this video, we're going to talk about what is AI. The beginning of AI, or intelligent machines, was all about telling machines what to do by establishing rules. If this happens, then do that. Knowledge systems underpin almost all of what we consider traditional if-then rule systems and refers truly successful artificial intelligence. They were invented in the 1970s and proliferated in the 1980s. Knowledge or expert systems provide a structure for capturing and encoding the knowledge of a human expert in a particular domain. For instance, this slide shows a simple weather forecast app. It has encoded a human's expert knowledge that if the forecast shows rain, the app will recommend that a human carries an umbrella. While the vast majority of technology today remains rule-based, these systems have limited capacity and flexibility in the modern internet-connected world. They simply cannot change fast enough to be useful for long, and they ultimately limit what people can do with information. For example, expert systems have been used for years to help doctors make the right treatment decisions. At the extreme, for a given set of inputs, an expert system will give one result that applies to everyone in the world. But now the goal of personalized medicine is to have as many results as there are people in the world. Of course, it isn't possible to encode rules for each person in the world. The only way to reach that goal is to create systems that learn themselves from the world around them, not just from the humans who created them. These types of if this then that applications are so common that we don't think of them as that intelligent anymore. Today, when we say artificial intelligence, we mostly mean machines that learn. Machine learning systems provide computers with the ability to learn without explicitly being programmed. Algorithms build models which then update and change as they are exposed to new data. Machine learning's history began in the 1950s, but recent progress is a result of convergence between the development of probabilistic tools in the 1990s and access to large data sets and powerful chips used for graphics processing in recent years. There are many ways that machines can rewrite their own programs. Most rely on some form of calculus or a statistical technique. All machine learning algorithms use data to train a model that can then make predictions or decisions against some performance measure. Data is the raw material, and the learning style depends on the type of data, the type of problem, and the type of algorithm. Performance is measured based on how accurately the program predicts a value for an output that was already known. The difference between the predicted output and the actual output is the error. There are various methods for programming a computer to adjust its function based on this error. Let's walk through 4 ways in which systems learn: supervised learning, unsupervised learning, reinforcement learning, and generative adversarial networks. Most machine learning algorithms are supervised learning algorithms, which make predictions based on a set of examples that are provided and labeled by humans. This means a human decides what data to use, called feature engineering, provide data to the model, called training data, and provides data to test the model against, called test data. In supervised learning, data is labeled with a value of interest, say a particular stock price. The algorithm looks for patterns in the values. It can use any information that may be relevant, financial results, weather, world events, to find a pattern. Once it finds a pattern, it makes a prediction for, say, tomorrow's price. Let's look at a potential real-world example of identifying images. In this case, fruit. In this example, a bowl contains 4 types of fruit. A human labels the input data, size and color, and the output data, the name of the fruit. The algorithm uses the training data to find clusters of similar shapes. Then a human tests these results by using a different set of data, the set that was held back for training purposes. The human tunes the model for optimal performance, gathers new data, and uses the model to make predictions. For instance, 2 cherries whose stalks are still connected are recognized as cherries. The second form of learning is unsupervised learning, or as we call it, humans learning from machines. Unsupervised learning uses different learning approaches and different mathematical processes to manipulate the data and provide a result. In unsupervised learning, data points have no labels, and the goal instead is to organize the data by similarity and understand its structure. There isn't a known result or correct answer, and a model is prepared by deducing structures in the data rather than testing against correct answers. An important goal of unsupervised learning is to get the machine to find data patterns that humans don't know about. Let's go back to the bowl of fruit. In unsupervised learning, the machine discovers characteristics such as size, color, and shape. The machine clusters the data according to the characteristics it has found and, as output, is able to identify 4 different types of fruit as well as count how many are in each class. The third form of learning is reinforcement learning, or as we describe it, machines learning from experience. Reinforcement learning is used in situations where the optimal outcomes are not known or are more difficult to define, and where there is less feedback. The feedback can be much later in the process and may not provide any information about the steps themselves. The steps have to be discovered through exploration, testing out a lot of different strategies and measuring performance against the long-term goal. In reinforcement learning, the algorithm is set up to make choices in response to each data point. A short time later, the algorithm receives information about the value of the decision it had made, called a reward, that it then uses to modify its strategy. Reinforcement learning is commonly used in robotics, including the software for autonomous or self-driving vehicles. It isn't possible to define the optimal path for a vehicle to drive. There are too many roads and too many obstacles in the world to define the positive result in every case. But we can define that success is staying on the road and failure is going off the road. Using reinforcement learning, the car will get a reward when it stays on the road, but it will not when it goes off the road. The car incorporates the feedback loop given the circumstances and builds its own model for how to drive to reach the defined success of staying on the road. The fourth form of learning is generative adversarial networks, or as we describe it, computers learning from competition. Generative adversarial networks, or GANs, are relatively new, introduced in 2014, but are considered one of the most interesting ideas in machine learning in a long time. GANs pit 2 neural networks against each other in competition, so that each improve their predictions through competition. The 2 competitors are called discriminative algorithms and generative algorithms. Discriminative algorithms map features to labels. So, given a series of features, what label would it give? Generative algorithms do the opposite. Instead of predicting a label given certain features, they attempt to predict features given a certain label. You can think of this in the world of spam. A discriminative algorithm will predict if an email is spam or not given the words in the email, while a generative algorithm will predict what words would be in an email if it is spam or not. Let's look at how these work in the world of images. The generator generates new data instances, while the discriminator evaluates them for authenticity against a dataset of known real images. For instance, the discriminator decides whether each image created by the generator belongs to the actual training dataset or not. The generator hopes that its synthetic images will be deemed authentic, even though they are fake. The goal of the generator is to generate passable images, to lie without being caught. The goal of the discriminator is to identify images coming from the generator as fake. So why would we use artificial intelligence? Humans are still more efficient and capable thinkers than machines in many ways, but we have one important limitation that computers don't have. We can't hold more than a few variables in our mind at any given time. We think in 1, 2, 3, 4, lots and lots and lots. Whereas computers can think in virtually unlimited dimensions using vast quantities of data. On this slide here is a 6D cube displayed in 3 dimensions. A computer knows that because it created it. I'm sure you did too, right? So how might we work together with machines? Machines can help us in 3 key ways. The first is retrieving and presenting information from the world around us in vast scale and speed. We're pretty good at perceiving the world. Machines, in many ways, though, are far superior. The second is learning. Learning is the process of taking that information that we've perceived and creating knowledge by understanding how that information could be useful. Machines can be quite helpful in learning as well, although they do have a key limitation. Machines are very good at understanding correlations. They're not very good at understanding causality. So we humans still have some superiority in the learning category. Finally, machines can at times help us understand how to act, how to apply the knowledge in some new and potentially unique scenario. This is the place where machines can be helpful, but we as humans still have far superior capabilities. Finally, when we think about what AI is, let's think about how we might experience AI. We break out this experience by 7 core experiences that reflect 7 human needs. The first is thinking. AI can help us think, meaning analyzing, making predictions. For instance, predicting what movie you'd like to watch or what product you might like to buy next. Second is knowing. An AI that creates knowledge and potentially establishes truth. For instance, an AI that can tell you if a crop is ready to be harvested based on satellite imagery, or an AI that might someday be able to tell you if a news article is true. Third is seeing. An AI that can see and extend our reality beyond the purely physical world. For instance, a face recognition system used by cruise lines to allow check-in without anything but a scan of your face. Fourth is talking AI, like Siri or Google Assistant, or perhaps something more focused, like the system for early childhood educators that allow teachers to report on things in the classroom simply by talking to Alexa. Fifth is feeling AI, AI that understands and expresses emotions. For instance, the in-vehicle emotion recognition systems that monitor the emotional state of drivers and riders. Next is AI that moves, whether it be warehouse robots, autonomous vehicles, or flying drones. And finally, AI that can help us make things, such as skeletal support systems for scoliosis patients that were developed by an AI-based system using non-human biological systems. We hope this quick synopsis of what AI is has been helpful. Please connect with us on sonderscheme.com or via email at hello@sonderscheme.com to learn more and continue the conversation. Thanks a lot.